And welcome to light. So tonight what we're going to be learning about is light, or more in reality, visible light. Okay, so what we actually see. Light is a part of an electromagnetic radiation, and what that means is that it's affected by an electric field and the magnetic field. Basically, the electromagnetic spectrum comprises of waves that travel in this type of a motion. These are known as transverse waves. Okay, some other examples of electromagnetic radiation are gamma rays, X-rays, radio waves, etc. The speed of light, as we've already learned in our formula with E equals mc squared, is going to be a constant 3 times 10 to the 8th meters per second, and that is when it is in a vacuum. In fact, all electromagnetic radiation travels at that speed in a vacuum. And the symbol, as we've already used, is a C for light. So there are a few definitions that you're absolutely going to have to know in order to understand how light travels and the wave particle aspect of it. So one thing is frequency, and frequency is just how often do you see it in a given amount of time. So think about if you saw your aunt frequently, that means that you would see them often in a given amount of time. If you saw them infrequently, you would see them less in that same amount of time. So that's frequency. Its symbol is this V type of symbol whenever you use a wave equation. Wavelength is using this lambda symbol, and what it is, it's the distance between two consecutive points on the wave, and I'll draw out a wave for you later so you'll actually understand that. But basically, wavelength is the length of the wave, and we typically measure it in meters or nanometers depending on what type of wave it is. Crest is the highest point of the wave. Trough, I always think of a trough like a pig trough. It's where they eat out of, and that is actually the lowest point of the wave. The origin is the source of the wave, so where does it start? And amplitude is the middle of the wave to the peak. So how high does it go? So let's look at this visually. So when we look at the parts of a wave, we have various crests in here. This is one crest, as we've already labeled. This would also be a crest. The troughs would be the bottom part. So here would be a trough, here would be a trough because it's the lowest point. Your origin is what you start with. Okay, so now what I'm going to try to do is I'm going to try to focus on wavelengths. There are different waves that you can measure wavelength. Number one, you can measure it from crest to crest. This would be considered a wavelength. That would be the exact same distance as if you went from trough to trough. Both are 100% accurate, and that would be a different way to measure wavelength. The last wave is for you to measure from when you go from one origin, okay, or when it's crossing the middle point, I guess, not the origin, through all the way so it completes one cycle. If you notice, this would be also a wavelength. Okay, all of these would measure the exact same distance, and they would all be measuring the wavelength, which would be meters, nanometers, centimeters, depending on, once again, what type of wave it is. The amplitude, notice that the amplitude is not the full height, but it is half the height. Okay, so it's basically, if you wanted to talk, it's from trough, I'm combining them, trough to crest, and then divide by 2. It's basically half of that distance. So what makes up the electromagnetic spectrum? It is basically, you've got your radio waves and your microwaves and your infrared. And as we go from left to right, the only difference really is the amount of energy. And as you go from left to right, your energy increases. So when we look at the visible light, which is the only part of the spectrum that we human beings can see, it goes in the order of low energy, which is your reds, to your high energy, which is your violets. So this is where we get that lovely Roy G. Biv. So red has your lowest amount of energy, then oranges, yellows, greens, blue, indigo, and violet. So it's increasing amounts of energy. Therefore, when you look at your ultraviolet, it has more energy than violet. Okay, that's why it's ultraviolet, so it's beyond violet. And that's with your UV rays that you're talking about when you go outside in the sun and you expose yourself to the UV rays of the sun. You're exposing yourself to more energy than visible light. Therefore, it can do damage on your skin. Okay, this is also the breaking point right here onwards is your ionizing that we talked about during the nuclear unit. And these guys would be your non-ionizing radiation. Okay, so how does this translate to other aspects of a wave? So the first thing is I would always highly recommend comparing the two extremes. So you've got your reds and you've got your violets. Okay, so red has low amount of energy, so that's this wave, and violet has a huge amount of energy, so that's this wave. So then what you want to do is I draw these two extreme waves, one with very low rolling things and one that's very, very high energy. And then I just compare them because visually I can easily identify their wavelength and frequency, but mentally, if I just try to analyze it in my head, I can make a mistake. So I would highly recommend that you draw two extreme waves and then compare their frequency, wavelength, energy, stuff like that. When I look at these two waves, it becomes very obvious that this one has low energy. Why does it look like it has low energy? Well, it looks like it's going so slow. Whereas this one down here is so high energy, right? So this one has high energy. Now what I want to do is look at my wavelength. This wavelength from here to here is obviously longer than this wavelength from here to here. And then if I look at frequency, if this is the same amount of time going from left to right, let's say it's a second, I obviously see this purple blue one down here more frequently. Okay, because I see a lot more crests, a lot more troughs than I do in the upper one where it's red. Okay, so that's what I'd recommend is you draw two different waves. Understand that red has the lower amount of energy, violet would have the higher, and then compare your wavelengths, your frequencies, your energies by just looking at the waves and being able to analyze it. All right, so where does this apply towards light and what we see and what we're going to be needing to do in this class? Well, what's really cool is that white light, which is what you see either from the sun or you can look at your lights like light bulbs. Okay, what you see is white light. And what it is it's made up of all the colors of the visible spectrum. So that's what's right here. What you can do is you can either use like a raindrop, okay, raindrop. You can use, or moisture. You can use these cool things called diffraction lenses. You can use prisms. I should say lenses, sorry. You can use spectral glasses. What these special things do is that they actually break up the light into their individual components. So even though we see white light, after it goes through a prism, what it does is it breaks it up into their individual parts, and that's where we get our Roy G. Biv. Okay, so our rainbow effect. So that's what happens is when you have white light and you pass it through a prism or a diffraction lens or a raindrop, you get these wonderful things, and this is called a continuous spectrum. And what that means is that it perfectly blends from reds to orange to yellows to greens to blues to violets. There are no breaks. But what happens is if it's not white light, if you, like, for example, heat up a gas, which we will be doing in this class, or heat it up through a flame, what happens is that these lights look a certain color. This one to me looks more of a purple, but when we break it down into their components, we actually see these individual lines being formed, and this is called a line spectrum. And what it does is it breaks it up into their different energy levels. Okay, so we've got our reds, we've got our violets. So this end right here is where the reds are is low energy drops, and this is high energy drops. Okay, and we will be seeing this in class we'll be using diffraction lenses. So what's really cool about this is depending on what gas you use, this spectrum result will be different. And how you can use this is you can actually look at these different spectrum and analyze them. And from their analysis, they're actually like fingerprints. Each element has its own specific fingerprint or spectrum, and you can tell from distances whether it's helium or hydrogen or lithium or any of the different elements. This is how we know what stars are made out of, because obviously we're not going to the star. So what we do is we use really expensive prism type things, and they are able to separate them into their line spectrum, and from there we can identify what elements are present on those stars and our sun. So these are just different elements, okay, and obviously by looking at them you can tell that they are all different and they are all unique. So one might represent neon, whereas the other one represents hydrogen, and you can tell that if, let's say, this was lithium and this was hydrogen, these are not the same element. Okay, so we would be able to look at through this and be able to look at a star and understand that either lithium was present or not present. These are called the atomic emission spectrum. So what does this happen? Well, this is really exciting. So what happens is we're going to talk about hydrogen, and we've got hydrogen right here. And if we put a little bit of energy into it, okay, and how do we put a little bit of energy? We use electricity. That's what happens with light bulbs. We use electricity. We can use flame. We could use the sun. What's going to happen is that this electron, which is currently in its ground state, meaning where it's naturally found, it's going to become excited, and it's going to jump up to different levels depending on what type of energy you added to it, okay? And this is known as the excited state, okay? But these electrons that are now up here in their excited state do not like that. So what they like to do is they like to go back down to their ground state, and when they do that, they release light in the form that we call a photon, and you will absolutely need to know that word is a photon. We never see this jump of going up in energy levels. What we do is we always see this energy drop down, because that's when we see our visible light in the photon. Okay, so here's an example that is showing you can have this electron, and it's going to jump to all these different levels depending on how much energy you put into it. And now at these other energy levels, these higher energy levels, it's considered excited. But it doesn't like to be there, so what it does is it goes back down to its ground state, and when it does that, it releases light, and we call this light, once again, a photon. So once again, we don't see this jump. We only see the drop going back down to its ground state. And the drop may not just be one step. So let's say that our electron went all the way up to this top level. What's going to happen is maybe it goes down to 2 levels, and then it goes all the way back down. Or it could go from one level down to the next, 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 and it just varies. Okay, so each of these, though, will release a photon. And this photon has a certain amount of energy associated with it. And that energy is translated to a specific color. So if it's a larger jump going all the way down, you're going to be more in the violet area. If it's a shorter jump like up here, you're going to be more in the red area, because the drop is not as much and the energy difference is not as much. So here's an image of the different possibilities of an electron dropping down. And what that does is it translates actually to these different types of light. So we've got ultraviolet, visible, which is what we can see. And then we've got infrared, which is what we cannot see. So if I go, so when you looked at that, it had all these different energy drops. Some of these we can see and some we cannot, okay, unless we have special glasses that actually do that. All right, hopefully you understand the process of light. Once again, we have an excited electron jumping, or a ground state electron getting excited by adding energy to it. It's in the excited state, doesn't like to be there, so it goes back down to the ground state, and when it does, it releases light in the form of a photon. The bigger the drop, the more closer to the violet you are. The shorter the drop, the closer to red you are.